Let us wait for a couple of minutes, 1 or 2 minutes. Then we can start. Okay, so today's lab objective is first part of DES cipher. Write a program to implement DES cipher. Are you able to see the screen? Can you see the shared screen? Okay, am I audible properly? Okay, perfect. So today's lab is about DES cipher. Okay, and you have studied this DES cipher in the previous second sessional examination up to seconds, and then after also I discussed certain parts. So this lab you have to implement only round function implementation. Okay, I will briefly cover this DES cipher basic structure and round function, and I will discuss you the implementation methodologies which you can consider for your implementation, right? And in the next lab, the remaining part of the DES cipher you have to implement. Okay, so let me go to the basic structure of DES. What is the basic structure of the DES? If we want to implement basic structure, see, encryption and decryption is done on a 64-bit block. Okay, so the input is 64-bit and the output is 64-bit. So plain text has to be represented as 64-bit. Okay, this is for the encryption input and this is the ciphertext. Okay, and similarly on the decryption part, the ciphertext is 64-bit ciphertext block is input and 64-bit plain text is the output. Okay, this is decryption and it uses 56-bit key, right? Now this is the basic structure of how DES performs encryption and decryption. The basic general structure of DES itself, how it performs encryption internally, that is this, right? So in here you can see that there is a 64-bit plain text input. It goes through initial permutation, then 16 rounds, okay, and then it goes through final permutation, and then it produces 64-bit ciphertext. Now, in each of these rounds, it uses 48-bit key and it generates these 16 keys through 56-bit cipher key, right? So there is a key generation. Now, this key generation was discussed later on, right? So at present, okay, let us go through the fundamental aspect of how this round is implemented. Right, so this initial permutation and final permutation are based on the static blocks. These are the initial and final permutation. Okay, so once we have 64-bit block, as per this initial permutation block, we have to perform the permutation. Right, that means in the initial 64-bit key, 64-bit block, what is stored on 58th bit, that is going to be stored as first bit in the initial permutation. What is stored on 50th bit location, so that has to be on the second bit position. So this way we have to perform the initial permutation. This is as per the theory. And similarly, after the round 16, we have final permutation. Okay. So final permutation, that means whatever is the output of 16th round, what is stored on the 40th bit, that has to be stored as the first bit of final permutation. What is stored on the second bit, 8th bit, that is going to be the second bit in the final permutation. So these initial and final permutations are as per this table. It is straightforward and simple. Okay. So implementation point of view also, it is straightforward and simple. For your implementation, it is not necessary to perform initial permutation and final permutation. And one of the major reason is, as discussed, is that there is not much significant impact of this initial permutation and final permutation on the encryption. Okay. So in that case, you may skip this initial and final permutation when you perform the encryption. Okay. Now, this round part, okay, this round function. So today's objective is round function. Okay, today's objective is round function. So which round function I am talking about? So round function comes in rounds. Okay, round 1, round 2, round 16. So you can see that DES uses 16 rounds, and each round of DES is a fiscal cipher. Can anyone tell me what is fiscal cipher? What do you mean by fiscal cipher? Can anyone tell? Inverting is possible. That is fiscal. Is this correct? Any other answer? Multiple blocks. No. Anything else? Both invertible and non-invertible element is there. And which element is non-invertible in this structure? Prince, very good. S box, Vimal, very good. So S box that comes over here, that is non-invertible. Other are invertible, right? Elements. So this structure contains both invertible and non-invertible, and so it is called as fistal. Similarly, what is non-fistal, that I discussed in AES for your remembering that what is the to understand the difference, what is non-fistal? Yes. Anybody? Non-fistal. I have explained you 2-3 times in last 3 lectures, 3 times what is non-fistal. If you have paid attention, you can answer. Okay. So non-fistal means all elements are invertible. Now let us come back to this DES. DES has this 16 round, and as you can see that this 64-bit input block, you can see over here. This is 64-bit plain text, right? So this goes through this initial permutation. So the output of this initial permutation is 64-bit. So this 64-bit goes as an input to round 1, okay? And all rounds have 64-bit input. Okay, so see, this 64-bit input is divided into two 32-bit blocks. This Li-1 and Ri-1. And the round has first input Ri-1 that goes to F. Now this f is our round function, and implementation of this f is our main objective for today's lab. Is that clear to all of you? F r minus 1 ki. Is that clear to all of you? Okay. So what you have to do is you have to create a function. Okay. You have to create a function, make your program modular, and create a function that has two input ri minus 1 ki. What is ri minus 1? The last 32 bits of input, and the first 32 bit of input that goes to the XOR. But to perform this XOR with li minus 1, we have to generate the output of f function. So today's lab objective is to implement this f function. So let us go through this f function. As you know that after this f function's output, it performs XOR with li minus 1, and that XOR is swapped as ri. So it is assigned as ri, and this one is assigned as li, right? So li, this is as per the equations which I discussed in the previous sessional. Li equal to ri minus 1 and ri is equals to li minus 1 XOR f ri minus 1 ki, right? So that is, these are the two equations. Now in that, what is f? That we ki, okay, ki is of 48 bit. Okay, ki is 48 bit. So that 48 bit ki is the input. See here, 48 bit key, okay, that is generated from 56 bit. So 48 bit ki you have to take. 48 bit ki you have to take. So you can keep for 16 round, you can keep 48 bit 16 keys. Okay. So you can store it in array. Okay. So you have K1 to K16 of size 48. So 16 cross 48 bit array you can take, and in each row you can store 48 bit key, which can be a random key. Okay. Now what happens with the 32 bit input? Now ri minus 1, see what is the input ri minus 1 length? 32 bit. Okay, and key is 48 bit. So that is not matching, right? So we have to convert this 32 bit into 48 bit. So this 32 bits goes as an input to the first element, that is expansion P box. What is expansion P box does? It converts this 32 bit into 48 bit. Right? It converts this 32 into 48 bit, and our key is of 48 bit, so that we can perform XOR, bit by bit XOR. Right? So you have to write a function f whose input is 32 bit ri minus 1 and ki of 48 bits. This ri minus 1 becomes 48 bit before it goes to the XOR operation through this expansion P box. So you have to implement the functionality of expansion P box. Now this expansion P box is as per this. Okay, you are already aware about that 1, 2, 3, 4, 5, 6, 7 and 8. 8 into 4, that is 32. So 32 is divided into 8 blocks, and then expansion is carried out. Now the expansion logic is same. 4 bit remains as it is. First bit is 32nd bit. What is stored on the 32nd bit, that goes as the first bit. And what is 5th bit, that becomes 6th bit over here, and 4th bit becomes 7th bit, right? So it is as per this table. See, in the table, first row is starting with 32nd bit, 1, 2, 3, 4, 5, and then 4, 5 again. Okay, 4, 5. So this comes here and this comes here. 4, 5. Then 6, 7, 8, 9. Then again 8, 9. Last two elements becomes first two in the next row. 8, 9 to 13. 12, 13, 16, 17. 16, 17, 20, 21. 20, 21, 24, 25. 24, 25, 28, 29. 28, 29. 31, 32, and then last element is 1. That is what is stored on the first bit that goes as the last. So if you see the length of this 1, 2, 3, 4, 5, 6, 6 elements in first row, and how many such rows? 1, 2, 3, 4, 5, 6, 7, 8. 8 into 6. So this becomes our 48-bit block, right? So from the same input, we have converted 48-bit expansion P box. Now, how will you write this code, right? So for expansion P box, so what you can do? Can anyone suggest? Can anyone suggest? We have to use this table, okay? This table you have to use. So you can write a for loop for I equal to 1 to 48, okay? Now your where your input is stored, 32-bit input is stored, it is, let us say it is stored in array, okay? Make initial row add plus 4 mod 32. Okay, there are different logic possible. Use auxiliary array. Perfect, Krishil. So there are different logic possible. One possible logic, which is the simplest logic I am discussing, that is you store this expansion, you store these initial values into some array. Okay, 32 bits in array. So you can convert it into single dimensional array. You don't need to put it into the matrix form. Although here we are representing it as a table, but the same table can be stored as one dimensional array. Okay, one dimensional array. So in the one dimensional array can be easily operated, right? Then you can take the index. Now what is this table indicating? That what is stored on 32nd bit, that should be stored here in the first bit, right? So our first element is obtained by the 32nd. So where you have stored, suppose you store it, let's say in some temp auxiliary array temp T, okay? So in T of I, okay, T of I, where you get the location, okay, so T of 32, T of I equal to 32. So T of 32 returns some value. Now that value has to be stored into this array. Using simple for loop and use this table as index. Yes, perfect. Yes, Priyank, you have understood, right? So this table can be represented as a one-dimensional array, and you can use this simple for loop. So it will become a simple implementation, right? You can use other logic also. You don't necessarily need to use this, but this is the simplest one. Okay. Now, what you have to do is, we have got, after this expansion P box, we have got this 48-bit output. So the output of expansion P box should be given as an input with KI to XOR operation. So you have to implement one XOR operation which has an input of this function's output, right? So you can store this expansion P box in some another array, one-dimensional array of 48 bits, and this KI can also be taken as one-dimensional array of 48 bits, and XOR operation can be performed. Okay, so if you are using C or C++, you can use function, and in Python you have some operator right? So with the help of that, you can perform the bitwise OR operation. So the output of this XOR now goes for S boxes. Now this is a interesting point. How to convert these S boxes? So S boxes are again given in the literature. So this is S box 1. Okay, is screen visible? I think I got disconnected and once again logged in. Okay. So this link I will share with you, and you can in the classroom I will share it with you. And here all the tables, right? These tables are given: IP, FP and IP are inverse, expansion function. So this is the table which we just now discussed. So you can directly copy from here because it is a standard table. Permutation. Okay, now these are the S boxes. Okay, see, all 8 S boxes are given. So in your program, you have to actually store these S boxes. Okay, so how will you store these S boxes? What is the size? 1, 2, 3, 4, 4 rows and 16 column. So you have to take an array of 4 cross 16. Okay, you can take an array of 4 cross 16 and store one S box. You have to take 8 such S boxes. Okay, so these you have to store, and directly you can take these values. So it will save your little bit time or typing time. Okay, so once you create these box S1, S2, S8 boxes, then you have to convert it. Okay, you have to apply this okay, yes, matrix. So suppose this S box 1 is present. Now what is the logic of S box? S box actually converts this 48-bit into 32-bit output. Why? See here. There are 8 S boxes and there are 48 bits. What was our input? Input was 32-bit. So the output should be of 32-bit. So here what we did, expansion. Expansion of 48-bit because we want to perform XOR with 48-bit key. So after performing 48-bit key XOR, we have to reduce the size. And for that we have S boxes. But in S boxes, we do permutation as well as we perform reduction, right? So here 48 bits are divided into 8 blocks. That means 8 into 6. So each box has 6-bit input, right? That means this 48-bit, you can create a for loop for I equal to 1 to 48 if I equal to I is greater or equal to 1 and I is and the AND operator or condition and I is less or equal to 6, then apply S1 box to get the output. Similarly for second S box, for I equal to I greater or equal to so if you take index 1 to 6, index 7 to 12, right? So all these will become input, and corresponding output of 4-bit you have to generate with the help of these tables, each table. So first output is going to be of 4-bit. The input is 6-bit. Now, how the input and output are generated? So, as you are aware that first 6 bits, out of first 6 bits, first and last, that means first and sixth bit. So, for I equal to 1 and I equal to 6, these two combination gives you row number. Okay. So if the input is in decimal, you have to convert it into binary, and then you have to take first and last bit as row number, and the middle 4 bits as column number. And so if you have this input 1 0 0 0 1 1, so first and last are 1, so 1 1 is 3, so third row 1 1 is 3, so third row, and 0 0 0 1 and first column. So the output is 12, and 12 output means binary. We have to convert it into binary. So binary of 12 is 1100, right? So this is going to be your output. So that output you have to generate here in this is going to be the output. Okay, so S1's output is 4-bit, S2, S3, S4 up to S8. Each S box produces 4-bit output, and so 8 into 4 is 32-bit. Okay, so this you have to generate, and so this 32-bit is going to be the output of S box operation. Okay, once the S box operation is over, then input goes to straight P box. Now, what is this straight P box? That is also given in the state permutation table, straight P box. Straight P box, it is given as table 1, 2, 3, 4 row and 8 columns. So 8 into 4, 32. So it means that after S box output is received, it is of 32-bit. So it will be in some table. Suppose you take one-dimensional table and then you use this state permutation table of 32-bit in one-dimensional. So this also you can store in one-dimensional. And then the same way as you have done it with the initial expansion P box, similarly here in the with the help of same permutation table, one-dimensional array, you can convert the output of S box into straight permutation table, right? So what is stored on 16th bit, that is going to be the first bit. What is stored on 7th bit, that is going to be on the second bit, right? 7th bit becomes second, 28th bit becomes third, and so on and so forth. So this way you have to generate the output. So this will be your straight P box output, and that has to be stored in some array. So the today's objective is to implement this f function, fri minus 1 ki. So this input you have to take static, key you have to take static, and then you have to perform all 4 operations. And this you have to use as a function which will be used in the next lab as round ones, or each rounds here, each rounds logic. Okay, it will be used in this logic. So don't write one main function for encryption and decryption. Create a modular function fri minus 1 ki with static values, so that you can modify it and use it later on in tomorrow's next week's lab for the implementation. Okay, is that clear to all of you? Have you understood it properly? Your problem definition, logic, everything was discussed. Okay, very good. Please go ahead and implement it nicely. Okay. This slide is already shared with you, and I'm also putting this link in the classroom. Okay, again, this might take huge number of lines when you will implement. Uh, so in that case, you may skip writing it into the journal. Instead of that, you can simply create the PDF as you have done it in the previous ninth lab, right? So you don't need to write in, you can simply put the code into that. I have already put this lab on the in the classroom, and this DES supplementary material, that link is also provided into that. So you can now use that and implement it. So here you are taking static input. So logic implementation should be proper. So for the static input, you will generate static output. Once it is done properly static, later on you can go ahead with the dynamic part. So make your program static for this.
Yes, hope you are doing.
Yeah, I have found that some students have not yet submitted their labs in the classroom. So yesterday we put the notice in the classroom, and I expect all of you who have remaining. There are only few students who are remaining, but they must finish their submission. Okay, some of you might be present today, so you should first do your submission if it is pending, and then also inform your friends. Already the message is put in the classroom. Yes, any update? Anybody? Anybody has implemented expansion p box part of the function? Expansion p box. Anyone has completed expansion P box and XOR? Yes, any progress? Anybody would like to show your progress? See, once this round implementation is done, this function is done, then encryption and decryption is comparatively less complex because the most complex part is in this round function. On for other steps of encryption and decryption, which you will perform in the next lab, uh, it will become easier. So you have to call it 16 times.